Okay, in this video I'm going to talk about the hockey stick identity, about binomial coefficients. So basically the identity looks like this. So for any k and n such that k is less or equal than n, we have this identity. So the sum of the binomial coefficient from or like j k for j from k to n, this sum is equal to a binomial coefficient n plus 1 k plus 1. Okay, so let's prove this. So the proof is going to be by induction, and induction on the difference between k and n. So induction on n minus k. So basically the base case is when k is equal to n. So the base case is when k is equal to n. So then we have the sum j from k to k, basically, because n is equal to k, right? jk, and this is we need to verify if this is equal to the binomial coefficient k plus 1, right? So this sum is only has only one term, and this term is k, the binomial coefficient kk, and so if this binomial coefficient is equal to this binomial coefficient, well, yes, they're equal because both of them are equal to 1, simply by definition, because the binomial coefficient is defined as, so the binomial coefficient and k is defined as n factorial over k factorial n minus k factorial, right? So the binomial coefficient, so let's say this one, kk, right, it's equal to k factorial over k factorial k minus k factorial. So k factorial and k factorial cancel each other, and k minus k is 0, so this is equal to 1 over 0 factorial, and 0 factorial is 1, so this is equal to 1, right? So yeah, so because both of them are equal to 1, so then this equality holds, and we can remove the question mark. So the base case is proven. So now the inductive step, right? So so suppose that the identity is true. The identity holds for like n minus k is equal to certain number d. Like consider for n minus k is equal to d plus 1, right? So what we have basically is well, we can simply consider it for n so this is equivalent to n equal to k plus d, right? And so we consider now the identity for instead of the number n, we consider like this value plus 1. So we consider it for n plus 1. So the whole identity now becomes the sum j from k to n plus 1 jk, and we need to prove that this is equal to the binomial coefficient n plus 1 n plus 2 now n plus 2 k plus 1. Yeah, so like let's write it more carefully. So we consider the identity for k and n plus 1. So like we have two parameters, k and n, in our identity, and so we keep the same parameter k, but we increase n by 1. So we consider it for this pair of parameters. Then their difference is d plus 1. So yeah, so we start from the sum on the left hand side. So the sum j from k to n plus 1 jk. So we simply take the first like all the terms except the last one, because this is the sum that would be for which we would be able to apply the inductive hypothesis. So the sum for j from k to n jk plus the last term is n plus 1 k, right? So now by inductive hypothesis, right? So by inductive hypothesis, this sum is equal to the binomial coefficient n plus 1 k plus 1, plus we have n plus 1 k. This term we keep it as it is, and this is simply for this we can apply the Pascal's identity, which I proved in one of the previous videos. So this is by Pascal's identity. So by Pascal's identity, this is equal to n plus 2 k plus 1. So, and this is exactly what we need. This is equal to this. So we started from the left hand side and we arrived at the right hand side. So this proves the inductive step and proves the whole identity.